Welcome everyone, and I'm really happy today to have Aaron Wagner from Cornell with us. And Aaron talk today is special because it's two parts. One part is today, and the next part is this Friday. And what I'm trying to do, starting with Aaron, is kind of a back to the basics kind of series, the basics in information theory and coding theory. So I'm really happy to have Aaron started. And Aaron's title is very interesting. So he's going to talk to us about what hockey teams and foraging animals can teach us about feedback communication. And again, this is part one. Aaron, so we're all waiting, and the Zoom stage is yours.
All right. Thank you, Salim. Thank you on many grounds. First of all, for organizing this online seminar series, which is a great service to the community, and was definitely before its time, or ahead of its time, when it was first conceived. And thank you also for the invitation to deliver this two-part talk on feedback. To be clear, the hockey teams and foraging animals come up in part 2 of the talk on on Friday. So the talk is in 2 parts, as Salim said. Today's talk is really just a tutorial on feedback. It's like a survey, and then Friday's talk is more of a proper research seminar, and the two sort of interface. So this talk will sort of set the stage for the talk on Friday. So yeah, it's about feedback and just point-to-point communication channels. So this is definitely a back to basics pair of talks. And I think if you haven't been following the literature on feedback, one might suspect that like this is an area where like everything was just settled in the 60s and 70s. There's nothing left to talk about. And certainly a lot was settled in the 60s and 70s, okay, to be clear. But at the same time, I think a number of interesting things have happened over the past 10 years that are worth talking about and kind of intriguing. So hopefully it will come out between today's talk and Friday's talk. So let's dive in. So, okay, there we go. All right, so, within information theory, we tend to think of communication as sort of an intrinsically one-way process, like unidirectional from transmitter to receiver, perhaps because we've all spent a lot of time like internalizing this like famous figure from Shen's 1948 paper, which depicts communication as a one-way street. And actually, if you do a string search for the word feedback in the 1948 paper, there are no hits. Okay, so feedback does not come up at all in the 48 paper. At the same time, in practice, communication is almost always bidirectional, right? Like if Alice can talk to Bob, then Bob can talk to Alice. It's actually hard to think of like, significant communication systems where the communication is truly one way, outside of like radio broadcasting or something. Even in storage, there's really a form of feedback, right? You can write something and then read it back immediately, and then, get a sense of what the receiver will hear later, right? So, perhaps really the fundamental model of communication we should have in our heads is something more like this, or maybe with a feedback link from the receiver to the transmitter as opposed to the received signal going back. Because this is really what tends to arise in practice. It's really two-way. Even if you're just trying to send information in one direction, right? You really have, usually like a two-way flow of signals. Okay. And, this was recognized, in the 50s. Certainly there were papers pointing this out and making the case that most practical systems have feedback. Shannon himself, was briefly aware of this. He wrote about feedback. He delivered the inaugural Shannon lecture, the theme of which was feedback. Okay, so it was certainly recognized, but it's easy to forget if you kind of, stare at that first figure a little too much. So this is the form of feedback we'll consider in this talk and in Friday's talk, just like ideal feedback from the output of the channel to the transmitter. Okay, and in practice, obviously, feedback's never quite so ideal, right? There's noise in this link, delays or whatever, but we'll focus on ideal feedback here. Okay, back to basics. All right, so what are the mechanisms by which feedback could be useful? Like suppose you have this link here, and suppose you just want to send information from the transmitter to the receiver. Okay, so how might this link be useful? Just qualitatively speaking, what are the mechanisms by which you could use the feedback link to facilitate the forward flow of information? Okay, so again, this is a classical subject, so people have uncovered various mechanisms. Okay, I'm going to focus, by the way, throughout this talk and Friday's talk on block coding. Okay, performance of block coding in point-to-point channels. Okay, so we're going to kind of draw a box around that. Okay, I'll say a bit about other models, but that's going to be the focus. Okay, so let's ask specifically for block coding, performance of block codes in point-to-point channels. How might feedback be useful? Okay, so first thing that comes to mind, okay, is that the channel has memory. then, you know, you can use the feedback to sort of figure out where the channel realization is headed and then kind of adapt your coding accordingly, right? So that's very natural. Similarly, if the channel is unknown, like if the distribution of the channel is unknown, right, then you can learn its law through training if you have feedback, okay? So the encoder can learn the law that way. Somewhat more subtly, okay, if the decoding time is not fixed, okay, then you can kind of decode early or late opportunistically. So if things are going well, you can kind of terminate the transmission early and kind of get credit for the unused time. And if an error seems likely, you can kind of persist the communication for a while longer to see if you can sort things out, okay? And feedback's needed for that, for the encoder to know what's going on at the receiver side. Likewise, if you have some kind of cost constraint, like a power constraint, okay, you can use the power opportunistically, okay? So if the communication is not going well, like blast away a lot of power, and hopefully that happens with low probability, so it kind of averages out in the end, and you kind of put the power where you need it, namely on the channel realizations that are likely to cause errors. All right, and then this is sort of an order of like, you know, most obvious to kind of most technical or most subtle. Okay, so it turns out if the rate is low, okay, then it's effectively like the minimum distance of the code that matters, and feedback can give you an effective minimum distance increase, okay? And that's pretty much the list, I would argue, okay? So, you know, having studied the classical literature on feedback in point-to-point, you know, channels for block coding, I kind of categorize all the papers as kind of using one of these 5 ideas. If you zoom out to beyond point-to-point channels, beyond block coding, then of course, you know, all kinds of new ways of using feedback open up. So once you're in networks, okay, that opens up a whole host of ways of using feedback productively. If you're doing control rather than just moving messages around, okay, then feedback's useful in new ways. If you care about complexity and not just the coding performance, then feedback can make a difference there, and so on. Okay, so this is not, it's not that these 5 items are just it for feedback. It's more like within this context, you know, I would argue this is kind of what's known. So we're going to draw a line here. We're going to draw a line somewhere, and we're going to draw it right there. So we're going to focus on just the ways that feedback's useful for point-to-point block codes. Okay. All right. So I'm going to go through all 5 of these mechanisms, and we'll do an example, and we'll talk about what's known and what's open in each of these contexts. And the sneak preview to Friday, okay, Friday's talk will provide a 6th mechanism. So a new mechanism is sort of qualitatively different from these 5 that's useful in this kind of classical context of point-to-point block coding. Okay, so we'll go through all 5 mechanisms. In order to talk about feedback and how it, you know, whether it beats non-feedback schemes or not, we need to talk about metrics. So let's do some notation now. So I'm going to set this problem up in the context of a discrete memoryless channel without feedback, and I think the extension to you know, feedback, and well, we'll talk about the extension to feedback explicitly, but the extension to channels with memory and continuous channels should be hopefully clear. Okay, so X is the input alphabet, Y is the output alphabet. We view the channel as just a stochastic matrix. We'll call it W. All right, so the message we'll view as a sequence of bits. So you have k bits you want to send. The encoder maps that to n channel inputs. Those pass through the channel, and the decoder then tries to guess the k bits. All right, this is about, as you know, if you want to go back to basics, this is about as basic as it gets, right? We'll do the feedback version of this. So the encoder observes the k bits. It outputs one channel input. It observes the channel output, and then can pick the second one, and so on. And then the decoder finally, after it observes everything, again, guesses the bit string. So the figures of merit we care about, there's the number of bits you're sending. There's the amount of time you're using the channel. There's a derived parameter, the rate, how many bits per channel use are you sending, and the error probability. We use the block average error probability. Okay, so you want the UK or IAD Bernoulli bits, and we care about the chance that the decoder guesses the whole block incorrectly, at least 1 bit wrong. Okay, so, you know, if you want to study feedback in point-to-point coding, I mean, you know, these are the metrics, and of course you can do like finite n analysis. You can, you know, say n is 2000, does feedback help or not? What error probabilities do I get? Those kind of studies are important, but they you know, they tend to be numerical. It's hard to say much theoretically, and it's hard to really kind of tease out the different effects that are at play with that kind of approach. So we're going to focus on just asymptotic figures of merit. Okay, so these quantities taken to different asymptotic regimes. All right, and there are actually different asymptotic regimes that people look at, And I think to really understand the feedback literature, you need to be kind of fluent in all of them, because certain mechanisms are kind of like most apparent or most useful in certain asymptotic regimes. Okay, so it's good to kind of know about all the different regimes that are out there. Okay, so there are four asymptotic metrics that we'll talk about. First one's capacity. Okay, so that's well known. So I consider that an asymptotic metric. And then there are others that all three of which you can view as like a refinement of capacity. So there's something called error exponents. There's something called the second order coding rate, also called the normal approximation. And then there's the moderate deviations performance, or just moderate deviations. Okay, and let me take a little bit of time to describe these, because again, it's to really appreciate, what feedback has to offer. You have to kind of understand these different metrics and how they relate to each other. Okay, so let's go through these metrics and then we can get to the mechanisms. All right, so to understand these metrics, I want to draw an analogy with I-80 sums. Okay, so it's possible to go any more back to basics, from like going over DMCs. Okay, it'd be I-80 sums. So each of these quantities has an analogy to a tail probability statement involving an I-80 sum. Okay, so and I think keeping that analogy in mind is useful for understanding these things. So let's pause the coding part for a moment and just think about I-80 sums. So suppose I have an I-80 sequence of random variables, zero mean, unit variance. Okay, so law of large numbers, weak law of large numbers says that the chance of making an order n deviation from the mean tends to 0 as n tends to infinity. The statement can be strengthened in various ways. Okay, so one strengthening is the following. For most random variables, this convergence is exponential. Okay, so there's some extra moment conditions here. Okay, it's not enough that the random variable just be finite variance. You need like a whole moment generating function, et cetera. But okay, for most random variables that arise in information theory, most distributions that arise in information theory, this convergence is exponential, and you can compute the exponent explicitly in terms of the distribution of the xi's. Okay, this is called the large deviations rate function. Okay, so it's large deviations, so that kind of tells you the speed of convergence here. The central limit theorem you can kind of also view as a strengthening. Maybe it's not a formal strengthening, but law of large numbers basically says the chance of making an order n deviation tends to 0 as n tends to infinity. The central limit theorem tells you what order has an order, or what order deviation has an order 1 probability, and it's square root of n. Okay, and you can actually determine the probability. It's the you get a Gaussian distribution popping out of this, so it's the Q function. All right, so all three of these statements are reasonably well known. What's maybe a little less known is the fourth one. So if you look at the central limit theorem and the large deviations, you can see there's kind of like a space between them, right? Like large deviation says, okay, the chance of making an order n deviation decays exponentially. The central limit theorem says the chance of making a square root of n deviation is order 1. And so you can ask, well, what happens if I make like an order n to the beta deviation, where beta is between 1 and 1/2? Like what happens then? It's somewhere between these two regimes, right? So you can study that. That's called moderate deviations. The idea being like order n is a large deviation, square root of n is like a small deviation, okay? And then this is like in the middle, right? Okay, so this is the statement. Okay, so if beta is between 1/2 and 1, then the chance that the sum deviates from the mean by order n to the beta, it tends to 0, and you can characterize how fast it tends to 0 in terms of the order and also the constant. Okay, so this is the Gaussian large deviations rate function. So if x is Gaussian here, you get an exponent, okay, and then that's the exponent you get here. Okay, so the moderate deviations statement, I'm quite fond of it personally. Maybe this is clear already. It formally kind of fills the gap between large deviations and the central limit theorem, right? I mean, it's not valid for beta equals 1, but you can just formally plug beta equals 1 in here, and then you get an exponential decay, right? I mean, you get the wrong constant, but I mean, it suggests the right exponential decay. Likewise, you can plug in beta equals 1/2. And then, this becomes an order 1 probability. Okay, so it kind of correctly predicts what happens at the endpoints. And, in form, it's sort of akin to the large deviation statement, but like the central limit theorem, the Gaussian distribution just kind of pops out of nowhere, right? So it kind of draws from both sides. Okay, great. So what does all this have to do with channel coding? So one way of thinking about the connection between all of these statements and channel coding is through the following lemma. And there are, many similar lemmas of this form. I quoted, an early one due to Shannon. I apologize for the extraneous semicolon there. But there are many in this vein. Okay, so the statement is if you have a DMC without feedback, for any input distribution P and any positive number theta, okay, through a random coding argument, you can create a code, or at least there exists a code with rate R, block length N, and error probability upper bounded by this expression here. Okay, and this quantity here is IID, with the joint distribution between X and Y being specified by, P and the channel together. Okay, so it's IID over time, and then, X1 and Y1 are jointly distributed according to this. And this is often called the information density. Maybe divided by N is the information density. Okay, so I'd suggest just ignoring the theta part. Okay, that's not really crucial to understanding the statement here. Essentially what this is saying is that like the error probability of the code is related to a tail probability of the information density. Okay, so I have an IID sum here. I care about a tail probability. That's my overall error probability. And so like all of those various theorems about IID sums, like you can apply to this IID sum, and then you get various statements about the error probability of the code. Okay. So, and there's a kind of analogous converse statement to this. There's like feedback versions and so on. So it is, safe to proceed with this. Okay, so for the information density, the law of large numbers translates to basically the capacity statement, right? If P is capacity achieving, then this sum here is IID with mean capacity, and R is presumably below capacity. Okay, so just divide by N, take the law of large numbers, and you're proving the capacity theorem using the law of large numbers. Okay, so likewise, okay, I can study the exponential decay of this thing with R fixed below capacity. That corresponds to error exponents. All right, I can have R approach C as like a, 1 over square root of N. So the deviation, overall deviation here from capacity is square root of N. All right, and then the central limit theorem will tell me something about the error probability that corresponds to the second order coding rate. And then you can also do moderate deviations, and we call that moderate deviations in information theory. Okay. So let me go through each of these just to state the definition so that it's clear what we're talking about. Okay, let's do error exponents first. So for any block length N and rate R, I can ask for the minimum error probability over all codes with that block length and that rate. Okay, so all codes that send K bits over N uses of the channel achieve error probability E, where my rate is at least R. And then we define the reliability function to be the exponential decay in the error probability as N goes to infinity as a function of the rate. Okay, so as long as the rate is fixed below capacity, okay, the error probability will tend to 0, right? And for most cases, it will tend to 0 exponentially fast, and you define the reliability function of the error exponent to be that exponent, okay? And the idea is as the rate approaches capacity, the error probability will still go to 0, but it goes to 0 slower, right? So the exponent will be smaller. And then as you kind of back off from capacity, you get like faster and faster decay of the error probability and the exponent increases. Okay, so you can give a whole talk, a whole like back to basics talk just on bounds on the reliability function. We're not going to dig into that here. I'll just say that this function is characterized for a range of rates close to capacity for typical channels, and then also in the very low rate regime. Like if R is very close to 0, then it's known how this thing behaves. But there's kind of a gap between the low rate and the high rate regime where there are relatively tight bounds on this function, but it's not known exactly. And this goes way back. All right. Second order coding rate is sort of akin to the central limit theorem. So define R and epsilon to be the largest rate you can get with block length N and error probability epsilon. Okay, so it's just sort of like the flip of this quantity. Okay, and turns out, for most channels, R and epsilon behaves like the capacity with a 1 over square root of N back off. Okay, and so you can define the second order coding rate for the channel, like the optimum second order coding rate, to be just that back off. So you just define it in a way that kind of isolates that constant there. So subtract the capacity, multiply by square root of N, and then it picks off the constant. So we'll call it the second order coding rate. Okay, and again, it's sort of like a central limit theorem in IID sums. That's the way I think about it anyway. All right, And without feedback, this was characterized by Strauss in 1962. And we'll say a bit about the feedback case later. Finally, moderate deviations. This one's my favorite, maybe for obvious reasons. Okay, so suppose the rate is backed off from capacity by epsilon n, where epsilon n goes to 0, but it goes to 0 slower than 1 over square root of n. Okay, so it's, again, between the error exponent regime and the CLT regime. Okay, then you can show that the optimum error probability is a function of the block length and your rate. It goes to 0 sub-exponentially, and you can characterize the order, the speed, and then also kind of the constant. This is a constant that depends on the channel that I won't define here, but it'll come up in the talk on Friday. It's like a variance quantity related to the channel. Okay, so that's the moderate deviations regime, and here the theorem is relatively easy to state, so I just put it here. Okay, and if I could just give, before we dive into the feedback thing, yes, Salim, please.
So I may have missed something. So why do you call it moderate here?
Yeah, it's like the well, first of all, it's just an analogy to the IID sums. I mean, in probability theory, they call this moderate deviations.
You had the beta there, but where is the equivalent of the beta? I may have missed it. So
beta. So the beta comes up in the second order coding rate. That's here, and there's no beta here in moderate deviations.
Okay, because
Sorry.
you see an n, so I thought this is kind of large deviation, or no?
You see what?
So there is the second equation is limit when n goes to infinity of log of p of e divided by n. So there's an n in the numerator.
Yeah, but this is going to 0 though. The epsilon n is going to 0.
Ah, okay.
Yeah, so your backup epsilon n is your back off from capacity. So okay. Yeah, if like epsilon n was like a constant, right? Then I mean the theorem doesn't hold in that case, but formally, if you just plug that in, if epsilon's a constant, then you get exponential decay.
I missed the fact that epsilon is a function of n. I missed that. Sorry.
Yeah, epsilon's a function of n. I'm sorry. Yes. Otherwise, it's just error exponents all over again. Yeah, good. All right. So just a quick plug for moderate deviation. So I would argue that moderate deviations kind of captures the engineering regime of interest better than the other two. So I'm a bit biased, okay, but this is my view. So just a quick plug on moderate deviation. So the normal approximation is nice in that like you're studying the regime where the rate's very close to capacity, which is what you want, right? But in the normal approximation asymptotic, the error probability is fixed at something that's bounded away from 0, and we like small error probabilities, right? Conversely, in error exponents, the error probability is going to 0 exponentially fast, which is awesome, right? But the rate is kind of stuck at something and bounded away from capacity. And we'd like the rate to be high, right? And in practice, we'd like the rate to be high and the error probability to be low, right? Simultaneously. And so you can argue that like the moderate deviations regime where the rate's approaching capacity and the error probability is going to 0 at the same time is really the regime kind of most engineering interest. Okay, you can make that case. All right. So enough of that. Let's move on to feedback. Okay. So so before I go through the mechanisms, and I keep putting that off, I know, but before we go through the mechanisms, I'd like to do like what I call a non-example, like a counterexample, if you will, that illustrates how in many cases feedback does not help, and it does not help in like a very strong sense. Okay. And that will kind of set the stage for all of our kind of positive examples that follow. So the non-example is the binary erasure channel. Okay, so the channel just erases bits with probability p. We'll consider the feedback version and the non-feedback version. Okay. Feedback version, there's a very simple scheme, right? You just keep transmitting a bit until it gets through, right? And then move on to the next bit, right? If k bits to send, channel takes 1 bit each transmission. So just keep sending each bit until it gets through and then move on to the next one. You can write down an exact expression for the error probability, right? So if Zi is an indicator for the ith bit getting through, so the Zi's are IID Bernoulli 1 minus P, it's an indicator that the bit gets through. Okay, so if all k bits get through, there's no error. If fewer than k bits get through, then the decoder has to guess for all the remaining bits, and you can write down an expression for the chance its guess is wrong. Total probability, you have an exact expression for the error probability, and it's basically just the chance that fewer than k bits get through the channel, right? You have like more than n minus k erasures. Okay, and this tends to 0 if n and k tend to infinity together, so long as the rate is below 1 minus p, so this achieves capacity. All right, so how would you do this without feedback? So, the standard way of doing it is just with a random parity check matrix. So just generate a big n by k matrix IAD uniform bits, okay? And then given your string UK, just multiply it with all the addition being modulo 2. You get an X string, you send that. The decoder observes like an erased version. So the decoder observes Y where some of the bits have just been, erased. So you just delete all those rows from the linear system. And then it just tries to solve the remaining system, okay? And this will work so long as the remaining matrix has full column rank, okay? So again, you can write, a relatively tight upper bound on the error probability, depending on how many bits get through. And you have the chance that like the generated matrix that emerges from that is not full column rank. And a union bound on this non-column rank quantity is reasonably tight in this case. So, so there's your upper bound. And this also tends to 0 as long as the rate is below 1 minus p. So it's capacity achieving. Okay. Moreover, I can study large deviations, error exponents, the central limit theorem, moderate deviations. I had pretty much IAD sums more or less in both cases. Okay, and they're all the same pretty much. Okay, so there's no improvement for error exponents, at least in the rate regime, or for a range of rates, near capacity. No improvement in second order coding rate, no improvement in moderate deviations. Okay, so feedback does not help, and it doesn't help in in any of these regimes. Okay, and it gets worse in a couple of ways. Okay, so it's not just the BEC for which this is true. Okay, in fact, for any symmetric channel, you can say the same thing. Okay, so there are various definitions of symmetry around. Here's the one that we'll use in the talk. This is kind of the standard one. I think it's what's in Cover and Thomas. So say a channel is symmetric if the matrix, the stochastic matrix, is such that if you take the outputs, i.e. the columns, okay, you can partition them so that within each partition of columns, okay, the rows are permutations of each other and the columns are permutations of each other. Right? That's true within each partition. So here's the BEC as a matrix, right? 2 inputs, 3 outputs. This is symmetric because I can partition it like that, right? And then here the rows and columns are permutations, and here too. And of course, not everything's symmetric. All right, so for symmetric channels, okay, then feedback does not improve, the capacity certainly. I mean, that's a discrete memoryless channel, but it also does not improve the error exponents for the range of rates near capacity. It doesn't even improve the order of the polynomial prefactor in front of the error exponent. Okay, so the error probability decays exponentially. The dominant factor in front of the exponent is polynomial in n. Okay, and you can show the order of that polynomial is not affected by feedback. Okay, it's not improved. Okay, so it's worse than just the error exponent not changing. Okay, that's the if you look beyond that, the prefactor is not changing either, at least the order of it. Second order coding rate doesn't change. The third order coding rate doesn't change. I won't define that, but you can probably guess how that works. Okay, look, one more term in the sum that also is not improved with feedback. Moderate deviations performance not improved with feedback. So yeah, essentially like every asymptote that we can compute, okay, feedback doesn't show an improvement for symmetric channels. Okay, so this is not looking good. For asymmetric channels, by the way, it's now known that the error exponent in the high rate regime is not improved by feedback. And this was actually, there's an interesting backstory to this. So this was viewed as an open problem for quite a while. And in fact, on a personal note, I'll say that I got interested in feedback as a graduate student, trying to prove this. Okay, so I thought this was open, and I was trying to prove it, and that's how I got involved in this area to begin with. I did not prove it, okay, but it's how I got interested in the area. Turns out there was a habilitation thesis by Augustine that showed this. It was not widely disseminated, so it was not widely known about. And I think it's fair to say like the original thesis wasn't very accessible. And so most people, myself included, didn't even know about the existence of this work until it came up in a session at ISAT 2010. And then there's some question about, whether it's correct or not. And Baris Nakabulu really did the yeoman's work of kind of going through that habilitation thesis and kind of checking everything out and then writing it up in a way that a moderate audience can, more readily understand and so on. So now it's understood that the sphere packing bound, as it's called, the upper bound on the error exponent at high rates actually holds for asymmetric channels with feedback. So that's one development that to me is very interesting, although I guess, in some ways it dates back to a while back. For asymmetric channels, the second order coding rate can be improved by feedback, not for all asymmetric channels, but for some, okay? And that will be the message of Friday's talk. And moderate deviations is open. Okay, so whether for asymmetric channels, moderate deviations is improved by feedback, we don't know. The evidence is no from what's out there now, but that's open. Okay, so at this point, I'll dive into the mechanisms. So I'd like to go through all 5 of these, and I'll say more about some than others. And we'll do an example of each one and talk about what's known and what's not known. This would be a good time to pause for questions if there are any questions about the background, the metrics, or the non-examples.
Maybe I have a small question. Is there a difference, because you mentioned there is an old proof by Augustine, I think if I'm saying correctly.
Yeah. And
is it Barish that did the 2019?
Yeah.
So is there a difference in the proof or it's just more written in the new language?
I'm not sure, to be honest. I have not read Augustine's work. I mean, I kind of paged through it when the PDF kind of became available, but I haven't really gone through it. So I'm not really in a position to say how much it differs. My understanding from my recollection of reading Barish's rewriting of it was that it was like essentially his argument, kind of, written in a more accessible way or maybe cleaned up a bit and stuff. And maybe applied, to things like the Poisson channel and stuff that Augustine, wouldn't have considered. But it was, I think it was basically Augustine's argument is my understanding.
Okay.
Yeah. Okay, so let's dive into the mechanism. So let's do memory first. So this is like the most obvious of the mechanisms, right? I mean, you ask any first year PhD student information theory, like how does feedback help? Memory comes to mind, right? And like it's maybe surprising that it's a somewhat challenging to come up with a good, clean example of this. Actually, given how natural it is, it's surprisingly subtle to try to illustrate this. So let me show you an example that doesn't work. Okay, the first thing that comes to mind is just like a BSC with memory, right? Like suppose you have a binary channel and you have like additive noise as mod 2 sum, and Zn rather being IAD, Bernoulli P is just some stationary ergodic process, right? So that seems like that should be like the simplest example where this works, right? Capacity is 1 minus the entropy rate of the noise, okay? And this doesn't work, okay? Feedback does not improve the capacity of this channel, even though it has this memory, okay? And here's why, basically on one slide. So you can probably read this faster than I can say it, but I'll say it nonetheless. So just consider the mutual information between the message and the channel outputs with feedback, all right? So decompose it as a difference of 2 entropies, chain rule. This is the definition of yi. If you know the message and all the past y's, you know all the past x's. So you can eliminate the x. And if you know all the past x's and the past y's, you know the past z's. You can throw that in. Okay, and then zi is a sufficient statistic for, the past of z is a sufficient statistic for zi, given all this stuff. So I can drop the u and the y. Boom, that's it. Okay, so, this plus Fano's inequality and, you've upper bounded the feedback capacity by the non-feedback capacity. Okay, so that didn't work, right? And it's not just the binary case, right? I mean, in general, it can be any size alphabet, right? So feedback does not increase the capacity of any discrete additive noise channel, okay? So you need to work a bit harder, okay? So here's an example. This example I came up with over the weekend. This may or may not be the simplest possible example, but here's one. So imagine a channel with 3 quote unquote states. Okay. So if the channel's in this state, okay, then you have, one input that passes through kind of noise free, and then 2 other ones that are kind of like completely ambiguous, right? Like, if you send one, you can't distinguish one from the other, but you can tell those 2 from the first one, right? Okay, and then the other two states are like essentially the same channel with just the symbols relabeled, right? And suppose the channel starts in a random state and then deterministically cycles, from 1 to 2, 2 to 3, and 3 to 1, just goes around and around like that. Okay. All right, so here feedback helps, right? So each constituent channel has a capacity of 1 bit, right? If this is my channel right here, right, then you can get 1 bit through that. With feedback, the encoder can learn the phase, right? And so the encoder and decoder together can learn the phase, right? And then, you can just always you can just timeshare, right, among these 2 channels and get a capacity of 1 bit. Without feedback, the encoder has no way of knowing which way, which state you started in. So it can't favor the right input at the right time. So it's forced to just use all the inputs equally. Okay. And that's mismatched, the wrong input distribution for each of these 3 states. And so you get a lower capacity. Okay. So, so channels with memory are closely related to unknown channels, right? I mean, certainly if you take like a Bayesian approach to an unknown channel and you say, I have some prior distribution over distributions of channels, then, your channel is quite literally just like a channel with memory. But, this example shows that like it kind of runs even a bit deeper than that. I mean, at some level, the 2 are kind of almost the same thing. All right. A question that might come to mind is like, well, why does feedback improve the capacity of Gaussian noise channels when it doesn't in the binary case? Like there's a whole section in Cover and Thomas on the capacity of colored Gaussian noise channels with feedback. So like, how is that different from what we just covered, right? So if you go through the same progression in the Gaussian channel, then this is what happens. This is the upper bound you get. This is using the fact that the Gaussian distribution maximizes entropy here. And you can hit this upper bound with Gaussian inputs, with or without feedback. Okay, so this is basically your quantity you're trying to maximize here. This term's independent of the input, it's just the noise, right? And the point is that, everything then boils down to like this determinant here, okay? It's like the power spectrum of the output, okay? And you want that to be white, like through, because of Hadamard's inequality, like the diagonal entries of this matrix are constrained by the power constraint. And you'd like it to be diagonal, because that will maximize the determinant for a given trace. So you'd like to kind of whiten the output, all right? And the point is you can do that better with feedback than without, okay? Whereas in the binary case, you just upper bounded this by like 1 bit per channel use. And of course you could hit that with an IID uniform input, and so there's nothing to do. Whereas in the Gaussian case, there's this power gain you can get. Okay, so feedback capacity for a Gaussian channel is very much like a power allocation kind of question. You quickly reduce it to just this problem of maximizing this, and now it's all about kind of maximizing this determinant, like trying to whiten the output as best as you can. Okay, so it's very much a power allocation thing, and in the vein of advances in the past 10 years, the capacity of the kth order ARMA Gaussian channel was found by Young-Han Kim in 2010. He also had results on the general stationary version and so on, but this has been open for quite a while. All right, so that's channels with memory. I'm going to skip the unknown channel case because that's, as we saw, that's kind of very intimately related with channels with memory. So let's move directly to the opportunistic use of resources. So we'll start with opportunistic use of time. Channel inputs, channel uses, and then we'll talk about use of power. All right, so the number of channel uses have been, there's this, you get channel uses, and then, the music stops, and, you need to end. In practice, for some transmissions, you might wish you had more than N transmissions, more than N channel uses. And then for some, you might be able to get away with, for some transmissions, you could get away with fewer, right? Depending on, the noise realization. So we can model that, right? So suppose the transmission ends at a random time N, a stopping time, meaning that, the decoder can tell at the termination point that it is the termination point, right? And then we can define the effective rate to be the number of bits you're sending divided by the mean of N, right? And if N is deterministic, this reduces to the previous setup. And this helps potentially a lot, actually. So go back to the BEC example. Suppose we just transmit each bit until it passes through, then move on to the next one. Let's let N be the number of channel uses it takes for all K bits to pass through. Expectation of N is just K over 1 minus P, right? Each bit is like a geometric distribution for the amount of time it takes, number of channel uses to get through. Okay, rate is K divided by the expected block length. So that's just the capacity. So the scheme's capacity achieving. Error probability, it's exactly 0, right? Because you don't end until all the bits have gotten through. Okay, so the decoder is never going to be uncertain about a bit. Okay, because you don't call yourself done until every bit has gotten through. All right, so you get a big change here in the error probability, and it comes about from just a very small amount of opportunism, right? Like n here is going to concentrate, right? N is just an IID sum, so n is going to concentrate around its mean, right? So like very small, allowing very small amounts of wiggle room in n translates to this like huge change in the error probability behavior, right? Okay, that's somewhat unique to the BEC. Okay. More generally, you can't just rely on a simple scheme like this. You have to do something like the following. So this is following Bernashef and also some kind of later, simplifications of his scheme. Given an arbitrary DMC, what you can do is, if you want to communicate at a rate below capacity, you first send the message using a non-feedback code. And since you're below capacity, that doesn't take up your whole kind of expected block length. All right. And then you just send an ACK or a NACK. Okay, so at the end of this yellow part, the encoder knows whether the decoder will decode the message correctly or not. And it can just send a 1-bit message for the remainder of the nominal block to indicate whether the message that it's going to decode from the yellow part is correct or not. Okay, and if it's correct, I should say, if the decoder receives an ACK, okay, then it just relies on the yellow part, it decodes, we're done. If it decodes a NACK, then you just repeat the process and do as many times as necessary. Okay, but the idea is that the chance that you have an error is exponentially small. And so it's like very low probability that you go to these later stages. Okay, and so they don't contribute to the block length, expected block length much at all. All right. So the error exponent for this was determined by Bernashef in '76, and it typically beats the non-feedback error exponent at all rates. In the moderate deviations in the CLT regime, those have both been studied, and we have conclusive answers. And actually, there's an order improvement. So not just the constants, but kind of the speed with which you can approach capacity, like in the second order coding rate regime, changes, and the kind of the order of the falls off in the moderate changes in the moderate deviations regime. Okay, so all three regimes are pretty well understood for this setup, and you get like a constant improvement in the exponent, and then an order improvement in the other two regimes. All right, so moving right along, let's do power. So the idea here is similar. Okay, there's a resource, it's power rather than time. Okay, but we're going to use this opportunistically. Okay, so we're going to kind of use it when we need it, and then not when we don't. The scheme behind this is a little bit more indirect, though. So in Bernashef's scheme, it's pretty clear you're kind of you're very explicitly using the channel uses more when you're expecting there to be an error, and in this case, it's a little bit more implicit. So, so here, this is mainly understood in the context of the Gaussian channel. So let's go back to the Gaussian case. So additive noise channel, white noise. And we have a power constraint, and the nature of the power constraint is kind of important here. So I wrote this out very carefully. Okay, so the constraint is for each message, okay, the expected power average over the block has to be at most P. Okay, this is not the only way of imposing the constraint, right? I could say this has to hold when I average this over the messages instead of for all messages. Or I could say for each message, this sum has to be less than or equal to P almost surely, not just an expectation. Okay, and these are different constraints. Okay, and they potentially give different different outcomes. But this is the one that we're going to look at here. Okay, so for each message, you have just an expected power constraint. Okay, so the scheme we'll talk about is the famous Schalkwijk-Kailath scheme. This is really good to know about if you've not seen it before. It's quite elegant. So here's how it works. So we have 2 to the k messages to send, right? K bits. So you partition the interval minus square root of p to p into 2 to the k intervals, equal sized. You assign your message strings to each one of the intervals and let theta of a message be the midpoint of its interval. Okay. And your goal is basically to communicate theta of UK, where UK is the message that you want to send. Okay, so at time 1, you send just literally that. Okay, so given the bit string, just compute the midpoint of the interval, and then just send that over the channel, right? That's a valid channel input. All right, the decoder will get a noisy version of theta UK, right? And so all you do in the remaining time steps is just refine the estimate. Okay, so the encoder knows the estimate through the feedback. So it can compute the error, right? It knows the true thing. It knows the decoder's estimate up to the current time. So it knows the error. So it can just take the error and just feed that back into the channel, right? And the decoder can use that to refine its estimate, and you just keep doing that again and again, right? And you choose this constant here so that you satisfy the power constraint, okay? This thing's gonna be falling, right? It's decreasing. And so the gammas are kind of, increasing to compensate. So you're always sending kind of, the right amount of power. All right, and then decoding is quite simple. Okay, you end up with an estimate of theta, and that's gonna lie in one of these intervals. Presumably, I guess it could fall off the edge, so, clip it. And then just output the string associated with the interval that you fell in. And that's that. And you can upper bound the error probability. This is not necessarily the tightest bound, but good enough for our purposes. And this is what you get, okay? And this is pretty wild, right? So rate has to be below capacity, so it doesn't improve the capacity, which is expected, okay? But it pretty much obliterates like every other asymptotic, all the other asymptotic measures are kind of obliterated by this, right? So if the rate is fixed below capacity, then this error probability decays to 0 as a double exponential, right? It's e to the minus 2 to the power whatever, right? If you want a constant error probability, you can approach capacity as 1 over n instead of 1 over square root of n, right? So you have a whole order change there too. And likewise in the moderate deviations. Okay, so this just blows everything open. Okay, but there's a catch. All right, and the catch is that it's using power opportunistically, and it's potentially using like a lot of power. Okay, when you have errors, like a lot of power. All right, so if you look at what the scheme is actually sending, I mean this was actually sent, right? So you can see it just naturally kind of automatically uses more power when you need it, like more power when you have an error, right? Because errors are associated with this estimate being off, which means the error is, this difference is big in magnitude, right? And so, if the estimate's already very good, then the encoder's not going to use much power because the signal is just low amplitude, right? And then, with errors, it's going to send larger and larger amplitude signals, okay? And yeah, the power really ends up being kind of through the roof if you kind of, do the analysis, and it's obviously not practical, and unfortunately that's sort of intrinsic to the scheme. So if you impose the power constraint almost surely, okay, then you don't really have this game you can play anymore, and you end up with just a regular error exponent and not the double exponential, and so on. And moderate deviations is just completely unchanged, and so on. Okay, so that's the Gaussian version. The DMC version of this, as far as I can tell, is just open. I could not find anything on a DMC version of this phenomenon. There's a natural approach to it, right? Like, you have a DMC with a cost constraint. The moment the channel starts behaving atypically, you just kind of like ignore the cost constraint and just blast away, right? And then, as long as errors are unlikely, that won't affect the average cost and so on. I think there's an interesting story there to be told, and seems to be open. All right, so with my remaining time, let's do the low rate case. So this is, again, kind of the most technical and the most subtle of all of them. So I'm going to explain this in the context of the BSC. So binary channel, additive noise, IAD noise, and consider it the low rate regime. So suppose K over N is fixed to be a constant as they both tend to infinity, but the constant is small. Okay, so the error probably is exponentially small. It's the error exponent regime. All right, so let's give a name to the code words, x1, x2, etc. And the decoding rule you can work out, you just map y to the channel output to the closest code word in Hamming distance, and that is the ML decoding rule. All right, so let's look at the error probability. Okay, so here's the average error probability, just average over the messages. I can do a union bound here, right? So if I send XM, the chance I decode XL instead is essentially the chance that XL ends up being closer to the output than the transmitted code word is, right? And that's got to happen for some L not equal to M for me to have an error. So there's my union bound. Okay. And then, average is upper bounded by maximum. The sum is upper bounded by the maximum times the number of terms in the sum. Okay. And you can prove a similar lower bound, right? I mean, the sum is lower bounded by any single term in the sum. Okay, so you can get upper and lower bounds that look similar. You got 2 to the k versus 2 to the minus k. But if we care about error exponents, this probably is going to be exponentially small. Okay, and if the rate is low, then like the exponent in 2 to the k versus 2 to the minus k doesn't really matter. And to kind of first order, the exponent in the error probability is just this pairwise, the worst case pairwise error probability. Okay. All right, so just focus on 2 code words. What's the chance that if I send one, I decode to the other? Well, that's the chance the channel flips at least half of the bits where they differ, right? So we can write that down. Okay, and then if you plug this in and simplify, okay, you get your error exponent is basically controlled by the minimum distance of the code. Okay, it's the distance between the 2 closest code words in the code, and that's what really matters at low rates. Okay, so most of the code words could be very far from all the other ones. Okay, but all it takes is like 2 code words that are close to each other to just dominate everything. Okay, because we're at low rates. Okay. So we call it the minimum distance of the code. How large can the minimum distance be? Well, if you have 1 bit to send, i.e. 2 messages, you can achieve a minimum distance of n, right? You just, all zeros, all ones. If you have a positive rate that's very small, okay, then you can achieve a minimum distance of about n over 2. Okay, and the idea is you just pick your code words randomly, and then 2 random code words will be at a distance about n over 2 of each other. And as long as you don't pick too many at random, you'll have n over 2 kind of all around. Okay. All right, so here's the key thought experiment now. So suppose near the end of transmission, a genie swoops in and it rules out all but one of the incorrect code words. Okay, so it goes to the decoder and says, okay, you only need to worry about these 2 code words. One of them's correct, one of them's wrong. I won't tell you which one's which, okay, but just focus on those 2 and pick one of those 2. Okay, and suppose it tells the encoder which 2 it's told the decoder. All right, so from then on, for the remainder of the transmission, okay, you can just do a head-to-head competition between these 2 code words. So you have all zeros versus all ones, right? And so that would be beneficial because it gives you like an effective minimum distance increase, right? Like in order to decode XL when XM was transmitted, the channel's gonna have to flip like a bunch of bits in this last stage here to kind of overcome this this distance that's provided by coding 1 to all zeros and 1 to all ones. Okay, so you get a gain from the genie, right? And the point is the feedback kind of provides something similar to this genie. Okay, so let me show you more detail. This is the last technical slide of the talk. Okay, so we're following Ziga and Guroff here. So at time I, suppose you compute the posterior probability of all the messages given the past, and you just greedily partition the messages into 2 groups, okay, to minimize the difference of their sum probabilities. So I'll just do an example. Okay, so suppose you have 6 messages and these bars represent their posterior probability given the past. Okay, partition into 2 groups just from the top down, okay, in a way that minimizes the difference of the sum probabilities among the groups. Okay, so first one, put it either place. This is supposed to be a transmitted message. That's why it's a different color. So we put that one here, right? And then you always basically take the next one and put it to the group with the lowest probability so far. So that one will go there. 4 will go here, and then this probability is less than this probability. So actually, both of these will go there. All right, and then if the true message is in this group, you send 0. If the true message is in this group, you send 1. And this will improve the low rate error exponent over the non-feedback case. And you can kind of see why, right? It sort of automatically does kind of what the Gini does, right? If near the end of the block, you have like just 2 code words you're trying to decide between, then those 2 code words will have a high posterior probability. All the rest will be small. And so this scheme will assign one of them to 0 and one of them to 1, right? And that will just sort of persist, okay, while you figure out which of the 2 is the correct one. Okay, so it's very similar to that Gini aided scheme. It's worth mentioning this being a symmetric channel, okay? Although you get a low rate error exponent improvement, okay, you do not get a high rate error exponent improvement. That's true for all symmetric channels. You do not get a moderate deviations improvement. That's true for all symmetric channels. You don't get a second order coding rate improvement. That's true for all symmetric channels. Okay, so this is kind of why we have this this qualifier here, right? For symmetric channels, there's no high rate error exponent improvement. Low rates can be improved with feedback. All right, so let's wrap up. So block coding over point-to-point channels. Okay, what are the mechanisms by which feedback can improve performance? Okay, well, you can exploit memory. You can learn the channel. You can use the airtime of the channel opportunistically. You can use power opportunistically. And you can get a minimum distance improvement. And classically, those were the 5 mechanisms. And preview to Friday's talk, okay? The point of Friday's talk is that there's actually another mechanism, okay, that in my mind is qualitatively different from all of these 5, that also gives you an improvement in the performance of block coding over, over DMCs. So that's Friday's talk. All right, thank you.
Thanks a lot, Aaron. This was a nice, can you hear me?
Yes.
Yeah, because my wireless connection was bad at the end. So this was a really nice summary of all the work in the literature. So I'm looking forward to Friday's talk to learn more about the second part. So if anyone has questions, please feel free to ask. Otherwise, we can just meet next on Friday. So I'll wait a little bit if anyone has questions about this part. Yeah, if there are no questions, so we'll meet on Friday then, Aaron. Thanks a lot.
We're good. Looking forward to it. Take care. Bye-bye.
Bye-bye.